Thank you all very much for attending. So this project is a joint work with Eduardo Perez-Richet, who's at Sciences Po in Paris. So in many allocation problems, such as allocating goods, prices, or money itself, designers actually screen agents based on some measured characteristic of score, right? And the thing with score-based screening is that it creates very strong incentives for candidates to either manipulate the measure or to invest in the underlying characteristic that is being screened. Okay? So, for instance, think of a regulator allocating green labels to firms. Firms could either engage in greenwashing, which corresponds to manipulation, or truly invest in emission abatement. Right? So while the study of allocation mechanisms in the manipulation case is quite well understood, it is less well understood how to design allocation mechanisms when agent can truly invest in their time. So this is the question that we basically want to seek to answer. So to do so, we consider a screening model where a continuum of agents with unit mass are endowed initially with some initial type, right, that is distributed on some interval that contains 0, and according to some CDF F. And the distinguishing feature of our model is that agents can actually choose a final type at some cost. Okay, so the cost depends on the initial type and on the final type that you choose. And so I will be more specific in a few slides about what kind of assumptions that we are making on this cost function. But think of this the initial type of the agent as a natural type. That is the type that he could acquire at cost 0. The principal, on the other hand, can allocate rewards of different values to the agents, can freely access such rewards. And we think of the highest value reward to be 1, and the lowest, and the principal can always give the agent a value 0 by not allocating the object, for instance. The principal cannot observe what is the initial type of the agents, but knows what's the distribution, and can observe and can condition, so target the allocation based on the final type that the agent is choosing. The payoff of agents is quasi-linear, so linear in the value of the reward. And so basically it's given by the value of the reward net of the investment costs. While the principal's preferences are given by some worth function, W, that captures what is the value for the principal of allocating an object of value R to an agent that invested in T and started from theta, right? And R0 is the exclusion value of the principal, that is the value that he assigns to unrewarded agents. So the important feature of this is that there are complementarities in the preferences of the principal in terms of the value of the reward and the final type. So the principal would like to allocate higher value rewards to agents that invested in the higher type. So for the sake of this short talk, I will just assume that the reward is binary. So think of it as approve or reject. That the value of the principal, the worth function, is linear and doesn't depend on the initial type, and that the exclusion value is normalized to 0. So the timing is basically as follows. So the principal commits first to a screening rule that depends on the final type, so that prescribes an allocation probability to the agents as a function of his choice of type. The agents observe their initial type and the mechanism that the principal committed to, and choose an investment strategy that maps their initial type to a new chosen type. Third, the agents are just approved with the probability sigma to theta. The principal's program basically consists in maximizing the expected final admitted type, subject to the agents choosing their investment optimally. Okay. So this is the type of cost functions that we are considering. So they are increasing and convex after the initial type and 0 before. So meaning that it's not costly to acquire a type lower than your initial type, while the cost is increasing and convex for after. So for the sake of this talk again, I'm just assuming that this cost function is quadratic, that simplifies a lot the analysis. And we define theta 0 by being the lowest initial type that would be willing to acquire final type 0 if he were sure to be admitted with probability 1. So under any optimal mechanism, agents that start with an initial type below that threshold would be excluded, okay, because they couldn't just acquire a positive type. So the relevant space for analysis is this theta 0 here. Right. So the second assumption that we are making bears on the distribution of initial types. Namely, we are assuming that the CDF admits a density function that is decreasing after theta 0, meaning basically that the principal is selective. So the lowest type that the principal would be willing to accept is 0, and the 0 lies in the upper tail of the distribution. So the principal is picky in that he wants to admit types that lie in the upper tail of the distribution. So very intuitively, one might think actually that randomizing the allocation might turn out to be optimal or good for the principal. So think, for instance, of deviating from this pass or fail mechanism that basically fixes a cutoff allocation, an allocation cutoff, sorry, T tilde, to some form of randomization where we create an additional step in the middle where agents are admitted with probability P. So initially, in blue is the indifference curve of the agent that is exactly indifferent between keeping his initial type, theta tilde, and bunching exactly at the allocation cutoff. So if we are randomizing, so in the first graph, all agents that are in the interval theta tilde T tilde are actually bunching at the cutoff, and all agents that are above are doing nothing and are admitted with probability 1. So randomizing has the benefit of inducing some of the agents that were admitted with probability 1 and not doing any effort in now doing some effort, right? But randomizing has also some drawbacks. It actually decreases the type that is indifferent, theta tilde 1, compared to theta tilde, and also induces some agents in the interval T tilde 1, theta tilde 2, not to invest. So those guys just have a too high cost to reach the second cutoff and are doing nothing and are admitted with probability P. Right? So it's not obvious. So even this seemingly very simple form of randomization shows that there are non-trivial trade-offs at play. What we show is that actually such a form of randomization is never optimal. Okay, so it has never any value for the principal. Our main theorem shows that there always exists an allocation cutoff such that the pass or fail selection allocation rule is optimal for that cutoff. So we think of this result providing some form of firmer foundation on the normative side for the use of pass or fail rules in selective environments where agents can actually manipulate their score, basically, and as providing a potential explanation for the widespread use of such rules. So very briefly on the extension, so we show that this result actually holds under fairly general conditions that bear jointly on the work function, cost function, and distribution of initial types. So we provide sufficient conditions such that cutoff allocation rules that allocate the lowest value reward before some cutoff and the highest value reward after that cutoff are optimal. So for instance, some examples of specifications that work are the iceberg investment, where the investment melts in the process, and Euclidean cost functions that are convex and increasing after the initial time. So we also investigate how the commitment power of the principal affects the payoff, and we show that both less commitment and more commitment yields exactly the same payoff. So it is actually without loss of optimality to consider only allocation rules that depends on the chosen type of the agent. So in the time that I have, let me give you an overview of how we prove that result. So first of all, as a preliminary result, we show that we can, without loss of generality, focus on monotone allocation rules. So allocation rules that are increasing after 0 and 0 before 0, okay, because there wouldn't be any benefit for the principal from admitting types below 0. So although it seems intuitive, actually it requires a proof because the allocation rule in our setting plays the role of transfers in standard screening models. So it involves a little bit of work. So given that, we find the indirect utility function of the agent. So this is the standard indirect utility, just the value function of the principal's optimization program. And given the quadratic cost function, we can decompose that problem as follows and define the value function of this inner maximization program as the pseudo utility of the agent. So this is a transformation of the true indirect utility, which is just the true indirect utility plus theta squared over 2. And given that it is the maximum over a family of linear functions, it's a convex function. And the envelope theorem readily implies that the derivative of this pseudo utility function is the investment of the agent. Right? And furthermore, we can re-express the allocation rule as a function of both the indirect utility and its derivative. So this allows us to rewrite the principal's program as a problem of calculus of variations, which is defined here, over a set of convex functions, so that are convex for the reason I just mentioned, sandwiched in between two bounds. So the minimal utility that agents could have, basically the utility that you have if you're rejected with probability 1 and not investing, and the utility U bar that you could have if you're admitted with probability 1 while not investing. Okay? U prime is also sandwiched in between two bounds. So since U prime is the investment of the agent, it just says that under monotone allocation rules, agents never invest in the type B below their initial type and never invest above the maximum type that they would be willing to acquire if they would be sure to be admitted with probability 1, okay, which is defined by the equation C of T bar theta, theta equals 1. Furthermore, the investment of agents must be increasing, okay, because the cost function is submodular. So given Topke's theorem, U prime must be an increasing function. So there's a monotonicity constraint as well. And the last constraint, 4, is just the probability constraint on the allocation rule. Okay? So this is the set of functions that we are optimizing over. So the thing with that problem is that it's kind of ill-behaved. So both the objective, so the objective is non-concave, and the set of functions that we are optimizing over is not even convex. So we need to innovate a bit. So a typical pseudo-utility in that space is looks like this. So it's a convex function that is sandwiched in between the two bounds that I've just defined, and must take off at some point from the lower bound at a type that we denote curly theta, and we call the takeoff type. So the derivative of that function gives back the investment of the agent and is pictured here. So the way we proceed is that we partition the sets of implementable utility functions into subsets that are parameterized by the takeoff type. Okay, so you can just consider the set of functions that are all taking off at the same exact point and decompose the problem of the principal into two maximization programs. So where the inner program maximizes over this set of parameterized function, and the outer program optimizes over the takeoff point. Okay, so think of the takeoff point basically as the first type that you admit with strictly positive probability. So what we show is that for any takeoff type, the set U curly theta is convex and compact, and that the objective function and the parameterized objective function is convex over that domain. So we know from Krein-Milman theorem and Bauer's maximum principle that we can find some optimum value at an extreme point of that domain. So the next step is basically to characterize the extreme points of that domain. And we show that some pseudo utility function is an extreme point of U of curly theta if and only if it is given by a countable sequence of bunching and resting intervals. So by bunching and resting intervals, we mean that, so for bunching, all agents in some interval are actually acquiring exactly the same types, so which corresponds to flat parts in the investment function. And resting intervals correspond to intervals where agents are keeping their initial type, so are not investing in any type above their initial type. So those regions correspond to regions, to parts of the function that are confounded with the lower bound theta. So given that pattern of investment, so the primitive of that function must look like something on the left. So that is given by thin parts where the investment is flat and quadratic parts where the agents are resting. So it's actually easy to see that such extreme points can be all generated by the class of simple screening rules. So screening rules that are increasing step functions, because you can always choose appropriately the steps such that it will induce agents before the indifferent agent not to invest, and all the agents in the interval that is in between the indifferent agent and the cutoff to bunch exactly the next cutoff. Right? So all extreme points can be generated by such step functions. So the last step of the proof just requires proving that among all of those extreme points, the one that corresponds to pass-fail is actually optimal. So this is so for the sake of time, I omit this part of the proof, but this is basically it. So to conclude, let me just give you a very high-level overview of how we proceed for more general cost functions. So in general terms, the indirect utility function of the agent is what we call the C transform of the allocation rule. And we say also that U is C convex. So what's special about the quadratic case is that C convexity reduces to usual convexity. So this is what buys us some practicability in that case. But we nonetheless show that even with general W and C, we can re-express the principles program as a problem of calculus of variations over that set of C transforms. So this problem can be challenging because the program is very ill-behaved again. So the objective is non-concave, and the set of C convex functions is not that well known and can even be non-convex. But we use some recent developments in the theory, from the theory of optimal transport, basically, and the theory of C convexity to extend our extreme point approach to more general cost functions. So I guess that's it for me. Thank you for listening.
Thank you. Questions?
For the monotonicity result on the allocation rule, were you exploiting that the density is decreasing, or is that not necessary for that?
No, we just proceed by contradiction. So assume that the allocation rule is non-monotone, then show that the upper monotonic envelope does better. It induces all the agents that were investing in a type below their initial type now to invest in a weakly higher type. And then show that reducing the allocation rule to 0 before 0 does better.
So then for the result that general mechanisms can't improve, you're also not exploiting those.
Sorry, what?
For you had the other result that general mechanisms can't improve when you could
so then we just use the taxation principle in fact. So from our recent paper by Vasiliki and Eduardo, so they prove a general taxation principle that proves that there is no loss of optimality using Meyersohnian mechanisms, basically. Thanks. Yes.
In which part of the proof do you use like the assumption on the density is like not increasing?
The assumption on what? Sorry.
In which part of the proof do you use the assumption like of the density function is not?
So yes, so I forgot to mention that. Sorry. So the density function being decreasing is important for the convexity of the objective. So it's a sufficient condition for the objective to be convex, actually.
And beyond assumption, when it's not.
So
decreasing.
So when the density is not decreasing, we actually don't know.
We have a couple of examples.
Yeah, so you can basically it makes the objective non-convex sometimes. So we cannot use the extreme point approach.